From the University of Arizona Distance Learning Program, this is Optical Sciences 505, Diffraction and Interferometry, with Dr. James Wyant. This broadcast is authorized by the Arizona Board of Regents on behalf of the University of Arizona. Any reproduction or retransmission of this course or use of same for granting of credit without the express written consent of the University of Arizona is strictly prohibited.
Well, I'll say good morning to everyone. Do we have any USC graduates in class? Okay. They've all dropped out? Okay, good. I was kind of worried for a second. I'm going to have a special exam today for them. I heard some rumor next week is a vacation week. Is that true? Well, we have to do something about that. And it turns out the week after next is when I take my vacation. I'm going to be out of town all week. And so we're going to do a couple of makeup class before the week after next. And the makeup classes are going to be next Monday from 11 to 12:15 and 12:45 to 2. However, you don't have to come. The good news is you can go off on your vacation. Don't worry about leaving me behind working and all this stuff. Because the tapes will also be shown at the regular class time the week after vacation week. So no one has to show up next Monday, but I thought I'd tell you about it anyway. One is, right, from 11 till 2 with a break for me to recover from 12:15, for you to recover from 12:15 to 12:45. But again, the tapes will be shown at the regular time the week after, a week later. Okay. Last class, there was a question from the back row, back there, about this 1 over I in the either the Sommerfeld or the Kirchhoff diffraction formula, and they're asking for a physical explanation of that 1 over I. And I've looked and I've looked and I've talked to people, and I still don't have a good answer for that. There's a little thing in Goodman in section 3.7 in the second edition. The first edition doesn't have it. The second edition, he says that 1 over I comes because the field P0 contributed by the secondary source at P1 depends on the time rate of change of the field at P1. And he shows that mathematically. But then I'm worried someone in the last row will ask, well, explain physically why that's true. And I don't know. I mean, I'm very intrigued by that question, and I'm going to keep pursuing it. But so far, I haven't found any book or anyone who can explain that to me. So, and if any of you find it, I would appreciate hearing about it. Okay, section 11.8 is what we're going to start out on today. Plane wave spectrum approach. Well, the first time I heard about this or read about it was in the first edition of Goodman's book, but it dates back sometime into the 50s, I guess. And also, if you go to Goodman's book, you'll find a reference by Ratcliffe, which is 1956, which he describes or talks a little bit about this plane wave spectrum approach. And I think this is a great way for looking at diffraction. It's very, well, the thing I like about it, you go through a little math, you get to use all that Fourier Transform stuff that Gaskell made you learn, and then you get some results, and you can look at the results, and you'll see physically what's happening, and it's very, very satisfying. So what we're going to do is we're going to take the complex field in some plane, and we're going to do a Fourier analysis of that. And we're going to see that when we do the Fourier analysis, the different Fourier components represent plane waves traveling in different directions. And we'll be able to calculate how far these various plane waves travel. And if we take into account the path differences for the different plane waves and calculate the phase shifts due to these path differences, we'll see that that is what the plane wave spectrum approach predicts for the phase differences between the different beams. So it's very, it's very satisfying physically. So let's start out here. We have, say, x, y, z. And we have some beam, propagating along here. And so we could say in this plane, we could write this as u of x, y, and say z is equal to 0. Okay? And what we want to do is we want to propagate this beam over here some distance, z. And so this is what we have. And what we want is u of x, y, and z. Okay? Well, we can write down here the spectrum. And we can say that in the xy plane, A f sub x, f sub y is equal to just the Fourier transform of u, x, y, 0, e to the minus I, 2 pi, f sub x, x plus f sub y, y, dx, dy. Okay, so we have the disturbance here, we know. We're going to calculate the Fourier transform of that disturbance, and we get A. Now, we also know that we could do an inverse Fourier transform. U of x, y, and 0 is the integral here of A f sub x, f sub y, e to the I, 2 pi, f sub x, x plus f sub y, y, dx, dy. And so we can do the Fourier transform, or if we had A, we could do the inverse Fourier transform and get back to U. Okay, well, maybe so what, but we'll see in a little bit why we're looking at this. The next thing we could say is, let's say we have a plane wave propagating along, and make it life simple, make it a unit amplitude plane wave. And let's say it's propagating with some direction cosines alpha, beta, and gamma. So propagating with direction cosines alpha, beta, gamma. And so we could write here this field B of x, y, and z. We could just write that as e to the ik alpha times x plus beta times y plus gamma times z. And for these direction cosines, we know that gamma is the square root of 1 minus alpha squared minus beta squared. Okay. Well, let's carry that on a little more and see if we can find something good about this. So we can say that if we go to some plane z equal to 0, we have e to the I, 2 pi, f sub x, x plus f sub y, y. If we have something like this, we can think of that as simply a plane wave. So this expression like this can be thought of as a plane wave propagating with direction cosines alpha is lambda f sub x. Okay. I think looking back at my paper, there's a mistake I left. I left something out here. I was checking to see if you were awake or not. I guess no one was. Should be a k in here. Okay. E to the I, k. Alpha x plus beta y plus gamma z. Okay. Missing k. Anyway, if that's, we put the k back in, and then we see that alpha must be lambda f sub x, beta lambda f sub y, and gamma, square root of 1 minus alpha squared, so 1 minus lambda f sub x squared minus lambda f sub y squared. Um, 2 pi where? I mean, we have 2 pi up here, e to the I 2 pi times f sub x, x plus f sub y, y. Is that the question?
Well, I mean, the f should be 2 pi times fx.
I factored out the 2 pi out in front up here. So back here, what we had b, whatever, is equal to e to the I k, so 2 pi over lambda times alpha x plus beta y plus gamma z. And then I just rewrote that. I said, well, let z equals 0. And so I rewrote that as e to the I 2 pi f sub xx plus f sub y, y. And that's true as long as alpha is lambda f sub x and beta is lambda f sub y. And gamma is 1 minus square root of 1 minus alpha squared minus beta squared. Okay, so anyway, these are just sort of some definitions so far. We'll very soon get to where we'll make good use of these. So what we could write here is called A naught of alpha over lambda, beta over lambda is equal to u of x, y. We're going to go to the plane where z is equal to 0. So u of x, y, 0. E to the minus I, 2 pi, and then alpha over lambda times x plus beta over lambda times y dx dy. So we basically just rewrote what we had earlier, writing it now in terms of an alpha over a lambda times x and a beta over lambda times a y. And this is what is called the angular spectrum of the disturbance u of x, y, 0. So this is called angular spectrum of disturbance u of x, y, and 0. So all we've done, we have simply written down the Fourier transform of the field we have in the plane z is equal to 0. Took the Fourier transform of that and wrote it in terms of the alphas and the lambdas and gave that a definition of the angular spectrum. What we want to do now, and so we claim we know u of x, y, 0. And so if we know that, we know A naught, we know the angular spectrum then, A naught, alpha over lambda, beta over lambda. And what we're going to try to calculate now is see if we can calculate how this angular spectrum propagates. And so is a propagation of the angular spectrum. And so we're going to look at a plane parallel to xy, a distance z away. So look at plane parallel to xy, but a distance z away. And so now what we would have, just copying this down here, we would have A, alpha over lambda, beta over lambda, z. So we take off the subscript here 0 because we're going a distance z away. And so that's going to be equal to u, well, Fourier transform here, but u of x, y, and z, e to minus I 2 pi alpha over lambda times x plus beta over lambda times y dx dy. So again, it's just a Fourier transform relationship. Right now we don't know u of x, y, z. In fact, that's the whole goal of this section, is to determine u of x, y, and z. No. I'm just doing the Fourier transform of whatever this disturbance is here. So now, I don't know what u is. I want to find that. And if I can find the relationship between this a naught, which I can calculate, and this a right here, then I could solve for u. So I'll write that down. If relationship between a naught of alpha over lambda, beta over lambda, and a of alpha over lambda, beta over lambda, and z can be found, then effects of wave propagation on the angular spectrum of the disturbance will be evident. Okay? So, we want to some way determine the relationship between the a naught, which we can calculate, and this a right here. And so let's see if we can figure that out. So let's go on here. In fact, I'll take a sip of coffee, help me figure it out. Okay. To find this relationship, what we're going to do is the following. To find desired relationship, note that u of x, y, and z is equal to integral here of a alpha over lambda, beta over lambda, and z, e to the I 2 pi alpha over lambda x plus beta over lambda times y, d alpha over lambda, d beta over lambda. Okay, just from the inverse Fourier transform relationship here. We know that this is true. Now the next thing we have to make use of is that this u here will satisfy the old Helmholtz equation. So let's write that down also. U must satisfy the Helmholtz equation. And my pen is getting a little dry, so I'll switch colors here. And so that's just what del squared u plus k squared u is equal to 0. So now we will take u and plug it back into the Helmholtz equation here. And after a little bit of work, not too much, we get d squared dz squared of a alpha over lambda, beta over lambda, and z, plus k squared, 2 pi over lambda squared, 1 minus alpha squared minus beta squared times a alpha over lambda, beta over lambda, and z is equal to 0. So just plugging this in here and grinding through, plugging this into here, grinding through, this is the equation that we end up with. And then we can write down that a solution to this equation is a alpha over lambda, beta over lambda, and z is a naught alpha over lambda, beta over lambda, e to the I, 2 pi over lambda, square root of 1 minus alpha squared minus beta squared times z. Okay, so this gives us a relationship between the plane wave spectrum at this plane z, well, z is equal to z, gives us the plane wave spectrum here in terms of the plane wave spectrum in the plane where z is equal to 0. And if we take, so we have this exponential up here, and if we take the case where alpha squared plus beta squared is less than 1, what we have then is simply that as these plane waves propagate along a distance z, we get a change in the relative phases of the various components of the spectrum. And each of these plane waves, I'll write this down in a second, but I'll state it first. Each of these plane waves is traveling at a different angle. And this phase change that we're getting is simply equal to 2 pi over lambda times the path difference that the different plane waves travel. So I'll write that down. This is kind of neat the way it works out here. So if this is true, if alpha squared plus beta squared is less than 1, the effect of propagation over a distance z is simply a change in the relative phase of the various components of the plane of the angular spectrum. And then what we go on and say, since each plane wave travels at a different angle, so each plane wave propagates at a different angle, each travels a different distance to reach a given observation point. And relative phase delays are introduced. Okay. So, just drawing a little diagram here. We have these two planes in space. Z is equal to 0, and Z is equal to whatever Z is, distance away. And in this plane, Z is equal to 0, we have these different plane waves, okay? Which we get simply by taking the Fourier transform of whatever the disturbance is here. And if we come over here at distance Z, well, these different plane waves are traveling at different angles. And so the plane wave spectrum we get here is simply the plane wave spectrum we had back here, where the different components have different phase changes due to the distance that they travel in going from here to here. And so once we get the plane wave spectrum over here, now if we want to find U in this plane, Z, we just take the Fourier transform or inverse Fourier transform of the plane wave spectrum, and we get the disturbance here. Now physically, I don't know, I find that very, that makes me feel very nice. That all I'm doing is just different plane waves are traveling different distances, and so they have different phases. That's all there is to it. Nothing beyond that. Well, there is one assumption I made here. Let's come back to that for a second. We said if alpha squared plus beta squared was less than 1. And what if that's not true? So if alpha squared plus beta squared is greater than 1, now we have the problem we're taking the square root of a negative number. So we're going to get an imaginary number. And so we would have then A of alpha over lambda, beta over lambda, and Z is A naught, alpha over lambda, beta over lambda, times e to the minus mu z, where mu was 2 pi over lambda, square root of alpha squared plus beta squared plus 1. So I simply went back to this, made alpha squared plus beta squared greater than 1, and we got another I, which multiplied by that gives us a minus 1. And we get this thing here, which means that these are, strongly attenuated. So these wave components are strongly attenuated. And what do we call these waves? Evanescent waves, right? So they're strongly attenuated, so as long as we go very far away here, we don't have to worry about them. Only very small values of z do we worry about them. So you see what we're doing when we propagate this plane wave spectrum? And we're just looking at the different paths that the different plane waves have to travel and calculate the phase change due to the different distances the plane waves are traveling. So isn't that a neat way of thinking about it? Yeah, no one's jumping up and down too excited yet. I don't know. I think after you think about it for a while, you will appreciate it and say, boy, is this neat. This is really, really neat stuff there. I think it's just a very, very, very nice way of thinking about the diffraction here. Okay. Now, I've heard some rumor going around here that there's someone in the class who thinks that if U of A plays Clemson, that Clemson will win. Is there any truth to that rumor? Is there someone here who is spreading that rumor? Any, what? That guy?
I don't believe I said that they would win.
Oh, now he's denying it. Now he's denying it. How about if Clemson played Utah? Okay, well, I just heard that rumor. I didn't know if there's any truth in it or not, but hopefully there's not. Okay, so there's a little bit more that I want to do here with the angular spectrum. And what we want to do is we want to put in some aperture. And we want to see what happens to the angular spectrum of the light. So this is simply, I don't give it a number, I guess, but effects, called effects of a diffracting aperture on the angular spectrum of a disturbance. And so we're going to put this aperture in the plane z is equal to 0. Put aperture sigma in plane z is equal to 0. Okay. So we're going to say that the angular spectrum of the disturbance incident on the screen is a sub I. So I'll just write that down. Let angular spectrum of disturbance incident on the aperture be a sub I alpha over lambda beta over lambda. Okay? And this aperture has the following transmittance function. T of xy is equal to, well, it's going to be a binary function. Either it's 1 or it's 0. So 1 is when xy is in the open portion of the aperture, and it's 0 otherwise. Okay. So now we're going to simply apply the boundary, the Kirchhoff boundary conditions. And so, I mean, that's simply saying that what's transmitted here, u sub t, still in the plane xy 0, we're just getting through the aperture, is what was incident times whatever the transmission function is for the aperture, t of xy. Okay. Well, let's see. So if we take this, we have a product here. And I'm going to take the Fourier transform on both sides. and I need help from you for this. Fourier transform on the left side is a sub t, alpha over lambda, beta over lambda. So that's just the plane wave spectrum of what was incident on the aperture. And the right-hand side is where I'm going to need some help here. Well, if I take the Fourier transform of u sub I will get the plane wave spectrum of what gets through the aperture. So that's a sub I. Now when I have a product here, and if I take the Fourier transform of a product, what does Gaskell say we get? A convolution. Yeah, must be right there. Okay. So we get the Fourier transform of u convolved with the Fourier transform of t. So I'll just call that capital T. Okay. And we'll just write down what capital T is here. You know, this little convolution theorem is one of the most useful things you run across. It's so handy. Oops. T of alpha over lambda, beta over lambda, is just a Fourier transform of whatever this aperture function is. T of x, y, e to minus I 2 pi alpha over lambda times x plus beta over lambda times y dx dy. Okay. So with this convolution of the spectrum of what was incident on the aperture times convolved with the Fourier transform of the aperture. Convolutions are difficult for me to do, and so I'm going to make life as simple as possible. And I'm going to say that what we have illuminating the aperture is a single unit amplitude plane wave of infinite size. So now if I take the Fourier transform of this plane wave, unit amplitude plane wave of infinite size, what do I get when I do the Fourier transform? A delta function. Good. So now a sub I, alpha over lambda, beta over lambda, is simply a delta function. And I know how to convolve delta functions. That makes life simple here. So we just convolve this delta function with this, and therefore what we get is that the angular spectrum of whatever is transmitted through the aperture is simply equal to the Fourier transform of the aperture. And so I'll write that down. The transmitted angular spectrum is found directly by Fourier transforming the transmittance function of the aperture. Okay. That's kind of neat, okay? And so what we can say here let's see, the smaller the aperture, the broader the angular spectrum. Okay? So if we try to send light through a small aperture, the light gets mad at us and tries to leave the aperture at a lot of different angles. Okay? And, well, we'll see that many times in the next couple of chapters. So that's everything I was going to say about plane wave spectrum. And as I said earlier, I think it's a very good way of looking at diffraction, and it gives you a nice physical feel as to what's happening. And you'll be amazed at the number of problems you can solve just thinking, let's see, I have all these plane waves leaving this aperture, and see how far do these plane waves propagate and going from z is equal to 0 to some distance z away. It works out very nicely. Any questions? Okay. Well, this takes us to section 11.9. I'm actually going to leave Goodman for a short period of time here. So you have to actually take notes. But we'll come back very soon, so don't worry. At least I don't believe. I'm sure this is in Goodman in some way, but I don't really follow his presentation directly anyway. And what we're going to talk about here is something that is pretty simple and extremely useful, called Babin's principle. And so let's say we have some aperture A, that produces a disturbance u sub p. So we're illuminating some aperture A, and someplace else in space we get this disturbance u sub p. Now what we're going to do is that we're going to break the aperture into two portions. A1 and A2, such that A is A1 plus A2. Okay? And we're going to say that A1 and A2 are complements of one another. And then I'll give an example. Okay. And as an example, well, maybe I can still do it on the same sheet of paper here. This is A. And so let's say that A1 is this portion, where this region here is opaque. And so this is A1. And A2 then, you can guess what A2 is. A2 is where, don't want to fill it all in, but maybe I'll have to. It's much easier to do this on a computer. Anyway, close enough. So these two are complements of one another, such that if I add A1 and A2, I get A. Okay. Again, you might say, so what? But this is the reason. If we go to, well, either Sommerfeld or Kirchhoff, I don't care which, so let's say Fresnel, Kirchhoff formula, it becomes clear then that the disturbance produced by this aperture is equal to the disturbance produced by A1 plus the disturbance produced by 2. Okay? Just when we do the integral over this aperture is equal to integral over that aperture plus integral over that aperture. And this is what's called Babin's principle. Okay. Now, I'll draw a box around that. So it's Babin's principle, shown in millions of books, I guess. Now, there's a special interesting case here, really kind of neat. So I'll say interesting case. If u sub p is equal to 0. Let's say we go to some place in our diffraction pattern where u sub p is equal to 0. So disturbance produced by light going through this aperture is equal to 0. Then u sub 1p is minus u sub 2p. So in that case, at locations where the disturbance produced by light going through this aperture is 0, the disturbance produced by light going through this aperture and disturbance produced by light going through this aperture, the amplitudes are the same, but they would be out of phase by 180 degrees. Okay. So in this case, the apertures give identical optical disturbance except they differ in phase by 180 degrees. Okay. Now, as you work interesting diffraction problems, and when you get to some problem you just can't figure out how to do it, remember Babin's principle, and often that will make it much easier for you. Question?
Going through aperture A1 and some energy going through aperture A2, and you measure nothing at aperture A, where does the energy go?
If I measured, I'm not sure of the question. If I measure, I have light going through A here, and I go to a single point, and it.
You don't have any light there. The case where u sub p equals 0.
Mm-hmm. Okay, I'm saying that for this interesting case here, the light going through here, there's some location in space where the amplitude is 0. Other places I have amplitudes. So there's only one location where the amplitude, well, there's a location where the amplitude is 0. And if I find that location, that means that at that location, the amplitude of the light going through this aperture and the amplitude of the light going through this aperture are out of phase by 180 degrees. That's only looking at one point in the diffraction pattern. This is the, I mean, this is the interesting case, but this is the more general case. Just u sub p is u sub 1p plus u sub 2p. So as I said, this is a tricky way of helping you I don't know if tricky is the right word, but it's a neat way of helping you solve complicated diffraction problems. Homework problems, in other words. Okay. Any other questions?
Yeah.
Mm-hmm.
So does that mean essentially if you like want to find the diffraction pattern caused by like A2 there, you know, the two white bars,
Mm-hmm.
you solve the problem for A1, or you kind of know what that is, and then you say that the diffraction pattern for A2 is the same, except for there's like a 180 view.
No, I'll emphasize again. What we're saying is that this is true only at locations where u sub p is equal to 0. Only at locations in the diffraction pattern where u sub p is equal to 0. This is true in general. So maybe for some reason I don't quite know how to calculate this, but I can calculate this one and I can calculate this one. So I could just take this, subtract from that this, and I get this one. This is true only at points where the field produced by light going through A was equal to 0. Did that answer the question? This is special case here. Only occurs at locations in the diffraction pattern where the amplitude for the disturbance produced by A is equal to 0. Well, we're not saying the transmittance for A is equal to 0. This is looking at, we have some, some diffraction pattern. And this is looking only at points in that diffraction pattern where the amplitude is 0. We have a lot of light going through here, and there's a lot of light in the diffraction pattern, but there may be some locations where we have zeros. A is an aperture, just some aperture. Yeah, don't confuse that with my previous angular spectrum. I just have some aperture A, some aperture A1, some aperture A2, and A1 and A2 add up to be A. This is always true. This is interesting cases only in locations in the diffraction pattern where the amplitude is 0. Some way, well, let me explain what by locations, okay? Let's say I have some aperture here. This is A, okay? And I come over here a distance z away. And maybe my diffraction pattern over here looks like, I'll do like this. It probably doesn't go up that much, but if I have some location over here where this is 0, maybe another location where this is 0, then that's when I can make use of this relationship right here. All other points in this field, I could make use of this relationship. So now do you understand this? A is some aperture, U is my diffraction pattern in this plane. So I think I made it much more complicated than what it actually is. Okay. Got it now? Ready to go on? So there's no one here from Nickel State. Am I right on that? Thought probably that was safe. Okay, chapter 12. We're going back to Goodman's book for a while, for 12 and 13 we'll leave the book again. But 12 comes right out of Goodman's book. And 12, we're going to talk about Fresnel and Fraunhofer diffraction. So far what we've gone through here, we've looked at, we said it was scalar diffraction theory. But we looked at it in its general form. So we looked at scalar diffraction theory in general form. And if we think about it, it was fairly general what we'd gone through here. And we assumed that the aperture was large enough that we could use scalar theory. And we assumed that we were looking at several wavelengths away from the aperture. And what we're going to do now is to use some approximations to look at these more special cases of Fresnel and Fraunhofer. And so what the expression that we got from above, let's refresh our memory here. We said u at some point p naught was equal to 1 over I lambda, integral over the open portion of the aperture. We're illuminating this aperture with some wavefront, so we call that u as a function of, I guess, p1, point in the aperture. And we had e to the I k r01 over r01. And we had some cosine factors here, depending on whether we used Sommerfeld or if we used Kirchhoff. And I'll just write down here cosine theta ds. And this is using Sommerfeld. So this is Rayleigh, Sommerfeld. And this was actually the G minus situation. And maybe I should draw a diagram. Probably should put something in here. And so we're looking over here in, say, a plane xy. And our aperture is over here in some plane, I guess I'll use squiggle and eta. So we have some aperture over here. And so this is sigma. And let's say we are a distance z away between these two, between the aperture and where we're looking at the field. And I'm looking here, doing the integral, looking right now at some point P1. And we're looking over here at some point P naught, where we're calculating a diffraction pattern. And there's some distance between P1 and P naught. And we call that R01. And this n here, the outward normal would be out this way. And I guess this theta angle would be here. We see that. So this was the result that we had so far. Okay. And I guess we could, normally, often this cosine of theta we pick to be 1. But we could write down here, in this case, that cosine theta is z over R01. And so we can plug that back into this expression right here and write down the result that u of P naught, but I'm picking a plane here, xy. So we say u as a function of x and y is equal to, we put in the cosine theta, we get z over r naught. So I get a z, which we could take outside the integral because it's a constant, over I lambda, integral over this aperture of u And we said coordinates in the aperture were squiggle and eta. And then we have an e to the I, k, r01. And we have an r01 here. And we get another r01 from the cosine theta. So we get an r01 squared. And then integrating over the aperture. Now I'll draw a box around that. I like that equation so well. Okay. So to get to this expression so far, maybe I should write down one more thing before I do this. I'll say that R01 from our diagram here, R01 will be the square root of z squared plus x minus squiggle squared plus y minus eta squared. Okay. Now to get to this expression here, I mean it took us a few days to get to that expression, but in getting here we really assumed two things. One was we assumed that the scalar theory is correct. And so this is really saying that the aperture is large compared to the wavelength. And two, we assume that we're many waves from the aperture. So R01 is many wavelengths. But those are really the only assumptions that we've made so far. And so that's my way of telling you we're about ready to make many more assumptions, okay? And I'll have some coffee so I'm ready to make these assumptions. Okay. Clean sheet of paper. So remember this equation. 12.1. Fresnel approximation. Well, what we're going to do here is that we have this terrible square root. And the R0 squared in the basement here doesn't bother us too much. And as long as we're many wavelengths away here, as far as this, the R0 squared in the basement here, I'm just going to approximate that as z, okay? But the problem we have is up here in the exponent. And the real problem we have up here is that R0 times k. K is 2 pi over lambda. Lambda is a very small number. And so small changes in R01 can make a huge change in e to the ik, R01. So while I can get away with just replacing this R0 squared here with z squared, up here it's a little more complicated. But I don't want to deal with this square root factor if I can avoid it. And so what we'll do is to go to the binomial expansion here, which we've used it several times this semester. And I personally love the binomial expansion. If any of you ever went back and looked at my old dissertation, you see the whole dissertation was a binomial expansion, one after another. I grew to love this thing. And so if we take the square root of 1 plus b, we know that that is 1 plus b over 2. And then the next term turns out to be minus b squared over 8. And there are other terms that you've all seen, but we're not going to worry about them. And so some way I want to use this binomial expansion here. And so what we'll do is we'll go to our expression for R01. And we know that z is going to be large compared to anything else. So I'm going to take z outside. I'm going to say this is equal to z times the square root of 1 plus x minus squiggle squared over z squared plus y minus eta squared over z squared. And then we use our binomial expansion here. And we say, well, that's approximately equal to z times 1 plus 1/2 x minus squiggle over z squared plus 1/2 y minus eta over z squared. And we'll forget the other terms, okay? We're going to assume here that z is large enough that we can neglect the other terms. And then we take this expression for R0, and we plug that into the exponent up here. And for down here, we just put in a z squared. And now what we get is that u of x and y is equal to e to the I k z over I lambda z integral over the aperture, but I'll take care of that by putting some aperture function inside here. U of squiggle and eta e to the I k over 2z times x minus squiggle squared plus y minus eta, supposed to be a y there, squared, d squiggle d eta. Okay. So we've gotten rid of the R0 up here, going through the binomial expansion, and we just get x minus squiggle squared plus y minus eta squared times k over 2z. And so what we have done here, I mean, what we have here is that we filled the aperture with all these spherical waves. And now what we've done is that we have replaced these Huygens wavelets by parabolic waves. Maybe I should write that down. So we have replaced the Huygens wavelets, or spherical waves, with quadratic, or if you like, parabolic waves. And we've done that many times this semester already. When we talked about spherical waves, talking about interference, we said, well, we're far enough away that we can approximate these spherical waves with parabolic waves. And that's what's called the Fresnel approximation. And so, if you're taking your prelims, and someone like me asks you what's the Fresnel approximation, that's it. We replace spherical waves with parabolic waves. Okay. A couple of other ways we could write this equation. And the first one, I don't know, Goodman likes to write it as a convolution, and I have to say that I don't I don't get very excited about this, but if Goodman says to do it, we'll write it that way. And then we'll write it the way that I like to write it, okay? So, as Goodman points out, we could write this as the integral of the form u of squiggle and eta, h of x minus squiggle, y minus eta, d squiggle, d eta, and where this convolution kernel, where h of x and y is e to the I k z over I lambda z e to the I k over 2z x squared plus times x squared plus y squared. Okay, so you can think of this as a convolution of u with h, where h is e to the I k z over I lambda z, e to the I k over 2z times x squared plus y squared. So that's one way of writing it. But the way that I like seeing this is the following. Just taking our expression we had up above and just rewriting it here in a nice little form. Make sure I have plenty of space. U of x and y was e to the I k z over I lambda z, e to the I k over 2z times x squared plus y squared. So I'm simply taking this and multiplying this out here. Okay. So we have this thing out in front times, and I don't want to run out of space there. So times the integral of u of x and y e to the I k over 2z squiggle squared plus eta squared. Okay. Times e to the minus I 2 pi over lambda z x squiggle plus y eta d eta, or d squiggle d eta. And so what we have here, we have this thing out in front, which is 1 over I lambda z times e to the I k z, so that's just a phase term that comes from propagating along the z-axis. And then we have this quadratic phase factor here, depending on x and y, or x squared and y squared. And then what we have in here is the Fourier transform of u e to the I k over 2z squiggle squared plus eta squared. And so what we have is simply the Fourier transform, oops, about out of time, Fourier transform of the product of the complex field just to the, before we get to the aperture, times this quadratic phase factor. Well, what we'll do next class, next Thursday morning, bright and early, we'll come back to this, starting out with this expression again, and thinking about it a little bit more, thinking about when this approximation is valid, and then after that we'll go on to Fraunhofer diffraction. So I'll see you bright and early Thursday morning.